Okay, now we want to look at typical sequences. First, we will look at a discrete memberless source. What is a discrete memberless source? A discrete memberless source is a source which puts out symbols of finite alphabet. The symbols are independent and identical distributed. Let's look at an example. So we look at a binary discrete memberless source with probability for 0, 2/3, and probability for 1, 1/3. Now we make an experiment. We generate sequences of length 18 and we write the sequences below. So we have this 4 sequences, A, B, C, and D. A is the all 0, B is a mixture, C is a mixture, and D is the all 1 sequence. What is your opinion? What is the most typical sequence? Of course, what we can do, we can calculate the probabilities. The probabilities can be calculated in this way. So 0 is more probable than 1. So in case A, we have 2/3 to the 18. This is 6.77 times 10 to the minus 4. The sequence B, we can count 9 zeros and 9 ones. So we have 2/3 to the 9 times 1/3 to the 9. That's equal 1.32 times 10 to the minus 6. Sequence C, we count 11 zeros and 7 ones. This is 5.2 to the 9 times 10 to the minus 6. And sequence D, we have all ones. So we have 1/3 to the 18. This is 2.58 times 10 to the minus 9. Of course, because 0 have probability 2/3, this is the most probable sequence A. But is it really a sequence which is typical? So what would you expect if you look at the source? I think what you will expect is that 2/3 of the symbols are 0 and 1/3 of the symbols are 1. And then if you look at our results, the most nearest sequence to this is C. So even if A is more probable than C, typical seems to be something like C, if you just do it intuitively. So here I write it down again. So the first sequence is the most probable. However, when you look at this, you will not surprise that C is the most typical sequences. This intuition, is it correct? We want to explain this. So in general, we denote by x to the n the finite sequences. So in the example, it would be x to the 18. So the ith entry is denoted by xi. So the first entry by x1, the second by x2, and so on. And they take values in x. In our example, this is a binary alphabet, so x is equal to 0 and 1. And we write x to the n for the Cartesian product of the set x with n times. So we have xn is an element of big X to the n. Now we introduce this notation here, NaXn. This denotes the number of positions of xn having the letter A, where A is in X. So for example, the first sequence we have here, if A is 0, 0xn is 18, and 1xn is 0, because there's no 1 and 18 zeros. And our intuition was that we expect that NaXn is roughly n times the probability of A. So let's look again at the sequences. So A, B, C, and D. So for its instance, the sequence C, if we count the number of zeros, they are 11, and the number of 1 is 7. So this seemed to be typical for this discrete memberless source. Now we want to choose a definition based on the entropy of a random variable x. So therefore, first we look how we calculate this probability. So I remind you, they are independent and they are all the same. For this reason, we can write them as a product. So Pxn of xn is equal to the product of Px of xi, where I goes from 1 to n, and in our example is 80. So this is the probability that xn was put out by the discrete memberless source Px. So sometimes we denote this because the distributions are all the same. We denote the distribution by Px to the n of xn, and this is the same. Now, of course, how do we calculate it? So it doesn't depend where the zeros and ones are standing, because we just count when we calculate the probability, the number of zeros and the number of ones. So we count here just how many zeros are there. So we count here Px of a, the number of zeros, and then the number of ones. And so if we have, like in the example, 11 zeros, so we take 2/3 to 11 times 1/3 to 7. There's some point you have to be careful a little bit. It could be that there's perhaps one symbol at the source which have probability 0. Of course, if such a symbol appears in a sequence, then its probability is also 0, because then one of the factors here is 0. So sometimes you have to be very careful, and for this reason, we take here the product only of the support of Px. The support of Px are only that element for which the probability is bigger than 0. In most cases, we will assume that for all symbols in X, the probability is bigger than 0. Now we assume that the number of appearance of the letter A in Xn is approximately n Px of A, n times Px of A. So that means if we just put it here in this formula, we replace this n A of xn by Px of A n to Pxa. So we just replace here this NaXn by n times Px of A. Now, I will remind you the definition of the entropy. So in information theory, you have defined the entropy, and you use it as some kind of insecurity measurement. So just let us note that the definition is minus the sum of all x and x, Px of x log Px of x. And if we just put it in, then this is equal to this equation. Let's look at this. Why is this true? I just change now my screen. I put on the white part, and then we will look at it. So let us see. So we have h of x is equal to minus the sum over all xn p x of x log p x of x. Sorry, we have to remove here. We just sum over all x, so I just remove here the n. So we sum over all x in x and get this. So we can rewrite this. Now we use the rules of the logarithm. So this we can write as the sum over all x, and then we have log px of x to px of x. Now the sum of logarithm is the logarithm of the product. So we can write this as minus log of the product of all x, and then we have here px of x to the px of x here. And now just to see it, that it's the same, or that the equation is 2, which we wrote there, we just write here 1 over n times n log the product of x px of x to px of x. And of course, this n goes here. So this is equal to what we want. So we have here 1 over n log the product over all x px of x to n times px of x, and we are done.